Okay, welcome to our first flipped lesson for the motion, forces, energy and momentum topic. Within SACE, this is sort of two topics, but I sort of combine it into one topic. They do forces and motion as one topic and then energy and momentum as a second topic. To start off with, we are going to look at motion and analysing motion. I'm hoping and I suspect a lot of this will be revision from stuff that we did last year in Year 10. But if it's not, that's okay. But hopefully you'll find a lot of this stuff you go, oh yeah, I've seen that before and I understand a little bit about that. Let's get into it. So the first thing that we need to consider is speed and velocity and how are they similar and how are they different. But before we do that, we just need to go back a couple of steps. As usual, here in the blue writing is our learning intention from the SACE board, and the things here in green are, if you like, our success criteria. They are the things that you need to be able to do. So here we're going to cover solving problems using velocity equals displacement over time, interpret solutions to problems in a variety of contexts, explain and solve problems involving instantaneous velocity of an object. So we're probably going to do a little bit more than that by way of background, but that's sort of what we're aiming at. So firstly, we need to understand the difference between a vector and a scalar. A vector is a quantity that has a size and a direction. For example, when we talk about a force. So if you think back to sort of middle school, doing sort of free body diagrams of the forces acting on an object, we'd represent them with an arrow. So the length of the arrow would indicate the size of the force, and the direction of the arrow would indicate the direction of the force. If we think about gravity, that's a force that's always exerted downwards. It always has a direction. A scalar is a quantity that has a size but not a direction. So when we talk about our mass, it doesn't have a direction. Later on, we'll talk about the difference between mass and weight. Weight does have a direction, and we may have touched on that previously. But things like mass, they don't have a direction. When we say, your mass is 71 kilograms, there's not a direction to that mass. It's just a scalar quantity. So from vectors and scalars, we go to distance and displacement. Distance is a measure of how far an object travels, and that is a scalar. It doesn't have a direction. Whereas displacement is a measure of the change of position of an object. It has a size and a direction. So if we look at this diagram here, we're starting off at this point here, going down to this point here. Say this was over a mountain. This is the path that we might take. That would be our distance covered. The direction is not critical there, whereas our displacement would be how much our position has changed from where we started. So that green line represents the change in position, which is our displacement. It both has a length or a size or a magnitude, but it also has a direction. So if we were using the compass there, that would be about southeast down there, like that. Often we would talk about, I often say this, but now most kids haven't heard this saying. My parents would always say, how far is it as the crow flies? And if you like that, as the crow flies, that direct distance is like the displacement. So a typical one I think of, if you're going to go to, and this is just very rough figures, if you're going to drive to Adelaide from, say, Tumby Bay, but it's similar for most places on Eyre Peninsula, it's going to be about a 600 kilometre distance travel. But you're going to have to go up through Port Augusta and then back down to Adelaide. The displacement between Tumby Bay and Adelaide is only about 250 kilometres, roughly due east. That's how far your position. That's how much your position has changed when you go from Tumby Bay to Adelaide. So, if you understand the difference between distance and displacement, and hopefully that's a reasonably simple concept, you basically understand the difference between speed and velocity, which is what we're talking about up here. Speed is the rate of change of distance. So if we drive to Adelaide, and let's say it's 600 kilometres, and we do it in 6 hours, we would say our speed is our distance, 600 divided by our time, 600 kilometres an hour. Our velocity is the rate of change of displacement. So if it took us 6 hours to get to Adelaide and it was only 250 kilometres, then our velocity would be 250 divided by 6. So that's actually going to be less than 50 kilometres an hour would be our velocity, because that is related to displacement rather than distance. Instantaneous speed or velocity just refers to whatever the speedo says at the time, if we use that analogy of driving to Adelaide. So whatever your speedo says at the time is your instantaneous speed or velocity. We can use them interchangeably there. Obviously, if you drive to Adelaide, your speedo is not going to say 100 kilometres an hour the whole way. You're going to be speeding up, slowing down, speeding up. So your instantaneous velocity is going to be changing. Your average velocity is the average rate of change of speed or velocity over a set period of time. So in the example there, we averaged 90 kilometres an hour on our way to Adelaide. So we were speeding up, slowing down, but that was our average. Now later on, and we did look a little bit at this previously, we're going to look at graphing motion, and I think when we look at graphing motion, you're going to see even more the relevance of instantaneous speed and average speed and velocity, but we'll come back to that later. Just few important notes here, and put these into the notes. Units. Our standard unit for distance and displacement is metres. So that means generally when we are talking about a problem, we don't always use the standard units. I was just talking about kilometres per hour there, but the standard unit is a metre. So generally that's the unit we will work in. The standard unit for time is the second. I was using hours there in kilometres per hour, but that's the standard unit is the second that we should be using, and the standard unit therefore for speed or velocity is metres per second. We can either write that as a metres /s, which means metres divided by seconds, i.e. distance divided by time, distance in metres, time in seconds. Or we can use this more indices scientific notation, which is ms to the -1, because basically -1 is basically the same as saying metres divided by seconds, because ms would be metres times seconds. If you put a -1 on an indice, that basically means it's on the bottom of a fraction. If you remember your indices stuff, maybe I will write that. So that's the same as writing m times by 1 on s, which is the same as metres per second, because s to the -1 is the same as 1 on s. That's from our indices type notation that hopefully you're familiar with. Also, need to be comfortable with converting units. Now, I always hope that this is a skill that students can do probably at about year 6 or 7, but sometimes it still trips us up. If we're converting kilometres to metres, we times by 1,000. There is 1,000 metres in a kilometre. If we're going from metres to kilometres, we divide by 1,000. 1,000 metres equals 1 kilometre. How do you go from 1,000 to 1? You divide by 1,000. Minutes to seconds, 60 seconds in a minute. So if we're going from minutes to seconds, we times by 60. If we're going from seconds to minutes, we divide by 60. If we want to go from hours to seconds, which we quite often do, times by 3,600. So 3,600 comes from 60 times 60, 60 seconds in a minute, 60 minutes in an hour. 60 times 60 is 3,600. So that's where those conversions come from. And if we want to go from kilometres an hour to metres per second, basically we want to go from kilometres to metres, so we times by 1,000, and then we want to go from hours to seconds, so we divide by 3,600, which is overall the same as dividing by 3.6. And if we want to go metres per second to kilometres per hour, we go times by 3.6. I tend to, just as a way that helps me always remember that, ride a push bike a lot, and particularly if I was on a road bike or something like that, often you're trying to sort of just average about 36 kilometres an hour, and it had a little ticker that ticked over every 10 metres. So if I was ticking over at every 10 metres, the seconds were ticking over by 1. I was doing 10 metres per second. That was 36 kilometres an hour. Another way to remember that, the world record for the 100 metres is about 10 seconds. they're running about 36 kilometres an hour. So if you remember 36 and 10, that sort of helps you remember the 3.6. That's just a nice little concrete way to remember the 3.6. So hopefully that covers our introduction into speed and velocity. So as I said on the previous slide, the velocity is equal to the displacement over time, or if we were talking about speed, speed is equal to distance over time. Now, one of the things that my expectation is that you can do now at stage one is that you can confidently rearrange formulas. And we've got this little 3-term formula, obviously, to start with. Now, my preference is that when you rearrange formulas, you do it with algebra, and the proper algebra way. I'll talk about an alternative that I'm not so keen on at the moment. It's not so keen on, but I know a lot of students do prefer. So firstly, sometimes we know the displacement and the time and we want to know the velocity, and then the velocity formula as is written works really well. But what about if we know the velocity and the time, i.e., we're going to drive at 100 kilometres an hour and we're going to drive for 3 hours, how far are we going to go? What's our displacement or our distance going to be? Well, that's how do we rearrange the formula to do that? So my preferred method is, well, we want to know S, so we want to get rid of the T. How do we get rid of the T? Well, actually, let's write it again out here. Whoops, I'm not on the thing I thought it was. V equals S over T. We want to get S on its own, so we're going to get rid of T. So we've got divide by T on this side, so we're going to times by T on this side, because T over T equals 1, so that'll cancel. Anything divided by itself equals 1. Whatever I do to this side, I've got to do to this side. Now, I use the little dot as a shorthand for multiply. I know that confuses some people, but probably get used to it because I can't talk myself out of it. Sometimes I try and show the multiplication. I'll try and do the right thing. I'll make it a multiplication. So T over T cancels, that equals 1. So we get left with S equals V times T, which is our second formula down here. So, yeah, that is just reinforcing that process of rearranging and how we go, because eventually we're going to want to rearrange some things that are a little bit more complex. Now, if we want to we know how far we've got to go and we know how fast we're going to travel, and we want to know the time to get there, which is obviously this formula down there. How do we rearrange the formula to get that? Well, if we do our V equals S over T, it's a little bit more complex. We want to get T, but T's on the bottom, so that's not very useful to us. So I'm actually going to start off by timesing both sides by T, and then obviously that cancels. Now I've got to get rid of the V on this side, so I'm going to divide by V. Whatever I do to this side, I've got to do to this side as well. V over V cancels, and that leaves us with T equals S over V, which is the formula that we have written down here. And obviously that one went to there. So that's just highlighting that process. I know that's a very simple equation to rearrange, and some of you are looking and going, why even showing this? Of course, we know that. But I do find that some people do get tripped up on that. Now, some of you may have had, well, I don't know what I want to say about those teachers, but some of you may have had teachers who taught you the triangle method, which is the other one that I've got written there. I'm not a fan of the triangle. I think you should learn to do algebra properly. But just to highlight here with the triangle, if you've learnt that, if you've got a formula like V equals S over T, you can write it into a triangle like this. So I'll actually write that down. V equals S over T. You can almost think of it like that. Now, if you use the triangle, the theory is, well, if you want to know what T is, well, T is equal to S over V. And if you want to know what S is, well, S is equal to V times T. I know some teachers use that method and teach that method. I know even in the new curriculum units of work from the department, they have that method. I'd prefer they just teach people to do algebra properly. But in the interest of being an inclusive teacher, I have shown you both methods there. But yeah, the expectation is that you're able to rearrange those formulas and use the rearranged versions of those formulas. Okay, so now I'm going to go through a problem. Now, it's a fairly simple problem. And I think I would hope most people would look at it and go, I can work that really easily. But I deliberately just want to show the process that I'd encourage you to go through when you're solving these problems. Because if you learn the process as you move into harder questions, I think that's going to really help you with the harder questions. So you might say, oh, this one, I don't really need that process. I can just work it out. However, if you learn this process, I think when we move on to more difficult calculations, it will really help you. So the problem, an athlete runs 400 metres north in 60 seconds, then turns and runs 200 metres south in 40 seconds. Calculate their speed and velocity. First thing to do is write down the info from a question and possibly, if you think it's going to be helpful, draw a diagram of what's happening. So to me, I'm going to write down the information here by drawing a diagram. So let's just start out with defining our direction, which we often do. So let's just say north is upwards on the page. And we've got an athlete. And they're going to run, oops, my thing just changed. They're going to run up here, which is 400 metres to the north. And then they're going to turn around and run back. Obviously, it's on the same path, but it's just easy to show. Draw an arrow there. Back to this point here, 200 metres. So yeah, just sort of illustrating what's happening there, the time that that's going to take them. Oh, sorry, let's do this here. The time here is 60 seconds. The time here is 40 seconds. So the total time is equal to 60 plus 40 equals 100 seconds. And the total, it's the distance in this case, the total distance is equal to 400 plus 200, which is equal to 600 metres. So going through that process of transferring what's written here in words into numbers and a bit of a picture. It's a really important step. Now, in this question, you probably could solve it successfully without doing that. But I just want to highlight at all, if you're stuck, this is your starting process. I think I've identified, often identify with students, the need to work on their problem-solving skills. This is the sort of strategies that are going to help people work on their problem-solving skills. The next thing is, and this is where it's almost like a job. This is all the information we've got. Actually, I've forgotten one important thing here, and I'm even going to do it in a different colour. What are we trying to work out? Well, our unknowns in this case are our speed, and so often I'll write that with a question mark, and our velocity. So there are unknowns in this case. So what we need to do next is find the right tool for the job. So what we're going to do is find the necessary equation. So it's a bit like you've got two bits of wood and a nail, and the thing you need to do is join those two bits of wood together. Well, what tool are you going to need to do that? You're probably going to need a hammer. So the tools in this case are the equations. So what are the equations that we know? Well, the equations that we know is that speed equals distance over time, and we know that velocity is equal to displacement over time. I don't think I talked about this earlier. I probably should have mentioned this earlier, so I'll say it now. V for velocity makes sense. T for time makes sense. S for displacement. Why do they use S for displacement? I can't tell you why they use S for displacement. Maybe they just want to confuse you. I'm not really sure. I'm not really sure why they use S for displacement. However, S is used for displacement. I guess you can't use D because D and distance and displacement would get confusing. So that's why we use S for displacement. So they're the tools for solving that. Then the final step, which is, I guess, what seems the most important step, but if you've done all that work, you'll find fairly simple, is you substitute the numbers in and solve. So in this case, speed equals distance over time. Oh, probably could have written T there. So that's going to equal 600 metres was the distance, divided by the time total, which was 100 seconds. So that is going to be equal to 6 metres per second. Now, because it's speed, we don't need to have a direction, because speed is a scalar quantity, so we don't need to worry about a direction. Velocity is going to be equal to displacement over time. So the displacement, we've got to come back and look at our diagram. We started off here, we finished off here. We are 200 metres north of where we started. So that would be our displacement. So that's equal to 200 over 100 seconds. The time is still the same there. 200 metres north over 100 seconds. And that is equal to 2 metres per second. But now that needs to have a direction, which is north. So that is just going through that process of solving a problem. And I acknowledge that's a fairly simple one, but if you get used to using that process, I think it'll really hold you in good stead for your problem solving. Okay, so for now, that's it for velocity. And now we're going to talk about acceleration. So acceleration is the rate of change of velocity. It's how fast or slow your velocity changes. If we almost go back, velocity is how, well, let's say just speed. No, let's go velocity. Velocity is how fast your position changes. Acceleration is how fast your velocity changes. So velocity is equal to displacement over time. Acceleration is equal to velocity over time, or your change in velocity over time. For those of you who go on and do some more complex mathematics, we would talk about the fact that velocity is the slope of a position versus time graph. It's the rate of change of position. And if you go on and do more maths, you would talk about that basically velocity is the first derivative of displacement, which derivative is a fancy way for working out slopes. And then you would learn that the second derivative, so the slope of the velocity versus time graph, which is what we call the second derivative, is acceleration. But if you're not doing any high-level maths, don't worry about that. But if you are doing high-level maths, that's a good little link to make as you go through that. But acceleration is the rate of change of velocity. Most commonly, well, let's talk about, because I didn't define these very well. So acceleration is A, VF is your final velocity, VI is your initial velocity, T is the time for it to change. Sometimes we use delta V because delta V is change in V. I probably should write that down. Really what we're saying there, delta V is equal to VF minus VI. So delta is a letter from the Greek alphabet. It's a triangle, and it's often used for change in. So where we talk about the change in something, we use that delta. So the change in velocity, we use that little triangle, the delta from the Greek alphabet, VF minus VI. Most commonly when we talk about acceleration, we'd probably talk about the acceleration of a car. We'd say, how long does it take to go from 0 to 100 kilometres an hour? That's, and we almost quote that as a time because we say, oh, this car will do 3.3 seconds from 0 to 100 kilometres an hour. But if we use our more scientific standard units, the units of acceleration are, I'm reading down the bottom here, whoops, that's not the right thing, metres per second per second. By how many metres per second does the velocity change each second? And if I do that in scientific notation, which I probably should have put on here, we will often write that as metres second to the minus 2. Because basically you've got seconds on the bottom twice. So that's the same as metres over seconds squared, which is basically the same as metres per second per second. So yeah, lots of different ways that you can look at those units. But generally we would write either metres per second like that, or ms to the minus 2. But they mean exactly the same thing. I think, if you know the initial, the final velocity, divide by the time, it's fairly straightforward to work out the acceleration. I don't think I have a problem on this next, but I might. I'll see when I get to the next slide. But we'll look at some problems involving these sort of things as we go on shortly. But take-home message, acceleration is the rate of change of velocity. Let's keep moving. So let's look at graphing motion now. And I must admit, during lesson we'll also use some motion sensors on the computer and do some sort of hands-on with this, and that'll probably help it make sense. But I think you can probably work out the sort of thing that we're doing to a reasonable degree from what we're going to talk about here. So what you need to be able to do is use graphical methods to represent linear motion. Linear motion just means motion in a straight line, including the construction of position versus time graphs, velocity versus time graph, and acceleration versus time graphs. We'll go through that in a sec. Use graphical representations to determine quantities such as position, displacement, distance, velocity, and acceleration. I'll show you how we do that. And use graphical calculation techniques to calculate the instantaneous velocity and instantaneous acceleration of an object. And again, I'll show you how we do that. So, firstly, a displacement time graph. So motion can be represented using graphs. In a displacement versus time graph, on the y-axis we have the displacement, which is the change in position, and on the x-axis we have time. So what this graph is showing, that started off at what we call the origin, where we start. After 1 second it had gone 1 metre. After 2 seconds it had gone 2 metres. Then it was stationary for 2 seconds, so the displacement didn't change, the position didn't change for 2 seconds. Then, now when the slope's going down, it's going in the opposite direction. So if the slope here was going up, that would be moving away. This would be moving back. So after 5 seconds, it's 1 metre from where it started, and at 6 seconds, it's back where it started. Then, it keeps moving, it doesn't stop here, it keeps moving, and at 7 seconds, it ends up 1 metre behind where it started. Then it stops for 1 second, and then it moves, in the next second, it moves 2 metres forward, and then another 2 metres forward, finally ending up 3 metres from where it started. So if I can sort of show this with the cursor, the object has gone, so start at the origin, in the first 2 seconds it's gone 2 metres, and then it stopped for 2 seconds, and then it's gone backwards for 3 seconds to minus 1 metre, then it stopped for a second, and then it's gone forward 4 metres over the next 2 seconds. So that's what that graph is representing. The slope of this graph represents the velocity. So what does velocity equal? Velocity equals displacement over time. The rise is the displacement the run is the time. You may have learnt that as, you may have used the word gradient instead of slope in maths. You may have talked about the change in y over the change in x rather than rise over run. I like rise over run. So we can work out the velocity. Now this line has a constant slope, so the slope doesn't change in these first 2 seconds. So we know the velocity is constant for the first 2 seconds. The slope gives the velocity. If the slope doesn't change, the velocity doesn't change. So what's the slope of this line over the first 2 seconds? Well, the rise is 2, the run is 2, so that is equal to 2 over 2, which is equal to 1 metre per second. Then let's look at what's the distance covered in the first 10 seconds. Well, we go forward 2 metres, then we go nowhere, and then we come backwards 2 metres, so we've done 4 metres, 2 plus 2 is 4. Then we go a further backwards a metre, so we've done 5 metres, then we go nowhere, and then we do 6, 7, 8, 9 metres. So 2 metres, nowhere, 3 metres through there is 5, 4 metres through there. The distance covered is 4 metres. Distance covered is 9 metres. What's the displacement? Well, the displacement is, for the first 10 seconds, how much the position changes. So we started here at 0, we end up at 3. So basically we are 3 metres in front of where we started. So the distance, the displacement for the first 10 seconds would be 3 metres. Now, because it's displacement, it's a vector, so it doesn't really matter. Let's just call that forward. It's important though to have a direction. So that's displacement versus time graphs. Now let's look at velocity versus time graphs. So now we have velocity on the y-axis, displacement, take that back, velocity on the y-axis, time on the x-axis. This graph is showing how the velocity changes over time. So what's this graph showing? This object is speeding up. After 1 second, it's doing 1 metre per second. After 2 seconds, it's doing 2 metres per second. After 3 seconds, 3 metres per second. After 4 seconds, 4 metres per second. So it's speeding up through that time. Then here where the line's flat, it's not moving. It's moving at 4 metres per second for the next 2 seconds. So that's a constant velocity of 4 metres per second. Then it starts to slow down. It slows down over the next second to 2 metres per second, finally slows down to 0. Then it stops. So this time here it stopped because its velocity is 0. For these 2 seconds, velocity is 0, so it stopped. Then it starts moving backwards and it speeds up as it does. So initially it goes 1 metre per second up to 2 metres per second backwards. Then it goes at a constant 2 metres per second for a second. Then it changes direction again and starts heading forward. Sorry, it doesn't change direction. Got that wrong. And this is a common mistake to make. It's going backwards at 2 metres per second here, and then it starts to slow down. And it slows down from 2 metres per second back to 0. Then at this point here, it goes from going backwards to moving forward. Up to 2 metres per second forward, 4 metres per second forward. Then again, 2 seconds, it goes constant speed of 4 metres per second forward. Then it slows back down to 2 metres per second and finally back to 0, or back to what we call rest. So that's what that graph is representing. The slope of this graph now, the rise over the run, now represents the acceleration. So if it's going at a constant velocity of 4 metres per second here, it's not accelerating, the slope is 0. So here it's accelerating. We can work out the slope by doing the rise over run like we did up here. But also we can work out the displacement from the area under the graph. So working out the area under that graph gives displacement. So firstly, if we were going to work out the acceleration at 2 seconds, so the acceleration at this point here, well, the slope is constant through there. So we can do this anywhere. Let's do it there. the rise is 2, the run is 2, the acceleration is equal to 1 metre per second is the scientific notation. So there's our acceleration. We might look at another one here. I haven't got the question here, but let's say we wanted to know what the acceleration was at 7 seconds. Well, firstly, can you see here, it's constant through that area, so we can go like that. It's not a rise, it's a fall. So the change in velocity there is minus 4 metres per second divided by the run, which is 2 seconds. Let's put units there just to make that a bit clearer. So that would be equal to minus 2 metres per second squared. So there's our acceleration. Now, if we want to work out the displacement, we work out the area under the graph. So let's go to a different colour here. We want to know the displacement up into 8 seconds. So if we divide this up, we've got a triangle, we've got a rectangle, and we've got another triangle. So the area of that first triangle is 4 by 4 by a half, because the area of a triangle is half base times height. So the area there would be a half times 4 times 4, which would be equal to 4 fours are 16, half 16 is 8 metres. Here, the displacement is the area of the rectangle, so that's equal to 4 metres per second times 2 seconds, so that's equal to 8 metres. And in this area here, it is 4 times 2, and it's a triangle, so we times it by a half. So that's equal to 4 metres. So the displacement here would be 8 metres plus 8 metres plus 4 metres, which would equal 20 metres. That's how we work out the displacement from a velocity versus time graph. We don't do acceleration time graphs that often. You might get an odd one in a question, but say if we looked at the acceleration versus time graph for the first 4 seconds here, well, that would just be a flat line at 1 metre per second, because that's what the acceleration was. But hopefully now you've got an idea of how we can work out things like position, displacement, distance, velocity, and acceleration from these motion graphs, both displacement versus time and velocity versus time. Let's keep moving. So in the previous slide, we looked at analysing motion using graphing, and now we're going to talk about the equations of motion, in particular the equations of motion at constant acceleration that we can use to analyse the motion of an accelerating object. And there's basically 3 of those formulas that we need to know about and use. The first is this formula here, Vf equals Vi plus At. So this formula lets us work out the velocity at a certain time if we know the initial velocity and the acceleration. The next formula is this formula here, Vf squared equals Vi squared plus 2As. So if you know the initial velocity of something and you know how far it's gone and the acceleration, then you can use this formula. So for example, if we drop a rock off a cliff, let's say it's a really high cliff, if we want to know how fast the rock's going after 3 seconds, we know the acceleration due to gravity. We'll talk about that in a sec. We know the initial velocity, it's probably 0 as you let it go. We can work out how fast it would be going after 3 seconds. This formula here, if we drop the rock off the cliff and we want to know how far it's going 30 metres after you drop it, you could use this formula here. And this last formula, remember S is displacement, which is like displacement or distance, lets you work out how far an accelerating object travels. So it's VIT, which is a bit like, if you just consider that first bit, displacement equals velocity times time, which is when you do constant velocity. But to introduce the effect of the acceleration, you add this half a t squared part. And again, we'll have a look at some of these in class. But again, it's going to be about substituting numbers into these equations, maybe rearranging these equations a bit, and basically using them to solve problems related to the motion of objects. And I will go through an examples of using these calculations in the next slide. So this year, in terms of these analysing motion and calculations, we're going to mainly just focus on motion due to gravity. And what you need to know is that any object that you drop near the surface of the Earth will accelerate at 9.8 metres per second per second. That means that after 1 second, it'll be going 9.8 metres per second. After 2 seconds, it will be going 19.6 metres per second because it gets 9.8 metres per second every faster. 9.8 metres per second faster every second. After 3 seconds, it'll be going 29.4 metres per second because it'll speed up again 9.8 metres per second every second. And that goes on. So let's look at this problem here. While celebrating her 18th birthday, a girl pops a cork off a champagne bottle, off a bottle of champagne. The cork travels vertically into the air. Being a keen physics student, the girl notices the cork takes 4 seconds to return to its starting position. How long does the cork take to reach its maximum height? So, a bit of a thinking question here as much as anything. Once an object is thrown into the air, as soon as it's left your hand, the only force acting on it is gravity. So as that object goes up, it is slowing down due to gravity. So gravity is acting downwards. It's slowing down. Gravity is the only force acting it. Gets to the highest point, then it starts coming down. Gravity is the only force again acting it. So gravity will slow it down at exactly the same rate it speeds it up. So basically it will take, if it's in the air for 4 seconds, it'll be going up for 2 seconds, then it'll be coming down for 2 seconds. So how long does it take the cork to reach its maximum height? Well, that's equal to 4.0 seconds divided by 2, which is equal to 2.0 seconds. Then it's asking us to work out what was the initial speed of the cork. So what's the information that we know? Well, we know, let's do each of these. We know that the acceleration, sorry, just accidentally muted my microphone. The acceleration due to gravity is equal to 9.8 metres per second, and that's downward. We know that the time it's in the air is equal to, the time going up is equal to 2 seconds from the previous. And this is a little bit tricky. You got to think about it. But the velocity at the top, the velocity at the final point, well, not at the final point, the velocity at the highest point will be equal to 0 metres per second. Why is that the case? Because it's on the way up. If we go back to this diagram here, on the way up it's slowing down, and at the highest point it momentarily stops. Then it starts speeding up, coming down. So that final velocity is 0 metres per second. So then we look at our formulas, and you'll get a formula sheet for these, both this year and again in year 12. But if we look at that formula sheet, so that's the write down the information step. If we look at the formula sheet, we will see there's a formula on there that says VF equals VI plus AT. We know A, we know T, we know VF, so we can work out the initial velocity, but we need to do a little bit of algebra. So we want to get rid of the AT from this side, so we get VI on its own. So I'm going to take AT from that side, because it's a plus AT. Whatever I do to that side, I've got to do to this side. So that leaves me, that basically plus VF plus AT minus AT leaves that. So we get left with VF equals VI minus AT. Sorry, that's wrong. Let me just find my undo button. Hopefully you see the mistake I made there. VI here is equal to VF minus AT. So VF we have said is equal to 0 minus, now the acceleration is going downwards. The projectile is going upwards. So we're going to call that minus 9.8. We're going to say downwards is negative, upwards is positive, because the acceleration works in the opposite direction to the initial velocity. 0 minus 9.8 times by 2.0, which is equal to 19.6 meters per second. Upwards, because it's positive. So that's how we work out the initial speed of the cork. Now, let's say we wanted to know how fast was the cork travelling when it was 1 metre above the ground. Well, using the same information we have there, but we now know... Sorry, muted my microphone accidentally again. So we now know in this case that the displacement for this part is 1 metre, and the other information all still applies. The formula we can use here is VF squared equals VI squared plus A times... not going well today. Plus 2AS, that was just on the previous slide. We substitute the numbers into there and we get VF squared equals 19.6, we just worked that out, squared plus 2. Now remember the acceleration is in the opposite direction, so 19.6 positive was up. So we're going to times this by minus 9.8, times it by the displacement, which is 1 metre. Okay, put that all in the calculator. We get 364.56. But remember that's V squared. So the velocity after 1 second, or VF in this case, will be equal to the square root of 364.56, which will be equal to 19.1 meters per second, and it will be still going up. So after 1 meter, it will not have slowed down all that much. What was the maximum height reached by the cork? Then we need to use the formula S equals VIT, this is our displacement one, plus a half AT squared. Substitute in the numbers there, S equals VI, which is 19.6, times by time, which is maximum height, so we only want on the way up, so that's 2 seconds. Then we go plus a half times by the acceleration, which is, remember, minus 9.8 because it's in the opposite direction, times by t squared, which is 2.0 squared. So put that all in the calculator and we should get that that comes out, it's almost a bit coincidental this answer, but it's because I think it's 2 seconds, 19.6 meters up into the air that it travels. Yeah, I'm pretty sure that's right. So that is how we use those 3 formulas for the equation of motion that I just talked about. Finally, this next one, it's a little bit of a trick question, but it does often come up. Describe the acceleration of the cork at each of the times after its launch. Well, after 1 second, the acceleration is minus 9.8 meters per second. Or you could say 9.8 meters per second downwards. Either way you want to say that. Because that's the acceleration due to gravity. It's after 1 second, it's still on its way up, but that's acceleration. What would it be after 2 seconds? Well, at 2 seconds, it's at its highest point. It's not actually moving, but guess what? It's still, the acceleration due to gravity is always the same. So it's still minus 9.8 meters per second. At 3 seconds, it's on its way down now. It's getting faster and faster and faster, but the velocity is coming down, so the velocity is negative, the acceleration is negative, the velocity is increasing, so the acceleration is still the same. The acceleration due to gravity is always 9.8 meters per second downward. That does not change. So hopefully that gives you an insight into what we need to do in terms of describing the motion of objects and the motion due to gravity. Sorry, it's probably been a little bit long, but hopefully that gives you the skills to work through the first part of this subtopic. Thank you.